Swayam Prabha. Digital India. Educated India.
Good morning, everybody. Today we will continue with our finite volume method to solve three-dimensional Navier-Stokes equations in complex geometry. In the last lecture, we discussed about the important geometrical parameters and the procedure of calculating convective fluxes. So today we will discuss about the diffusive fluxes. Now, diffusion flux of variable phi through the cell faces can be evaluated as the surface integral. This is basically diffusion coefficient uppercase gamma phi into grad phi dot ds. Now this operation grad phi dot ds over the confining surfaces will be summation of the again diffusion coefficient gamma phi multiplied by grad phi dot s, and this is basically over the all the surfaces that means over j, and j equal to eastern face, j equal to western face, northern face, southern face, top face and bottom face of the cell of interest of the control volume, the computational control volume of our choice. And so we can write it as finally summation of this diffusive terms. So any phase given by Sj we can write as alpha 1 into n1 plus alpha 2 into n2 plus alpha 3 into n3, where n1, n2 and n3 are three linearly independent unit vectors. They may be orthogonal, may not be orthogonal. Now when we operate grad of phi with this surface vector, we can get grad of phi dot alpha 1 n1 plus alpha 2 n2 plus alpha 3 n3, and through this operation we can get alpha 1 grad phi dot n1, alpha 2 grad phi dot n2, alpha 3 grad phi dot n3. Now if we define delta phi 1, delta phi 2 and delta phi 3 are differences of phi between two endpoints of the line segments delta x1, delta x2, delta x3, then we can write delta phi 1 equal to grad phi dot delta x1. Please note that this delta x1 and this delta x1, these are not same. This is bold and this defines a vector quantity, whereas this is the magnitude. I will come in detail in the next slides. So delta phi 2 is grad phi into delta x2. Similarly, delta phi 3 equal to grad phi dot delta x3. Now, as I mentioned in the last slide, that this delta x1, when x is bold, delta x2 and delta x3, here all the x's are bold. These are vectors associated with delta x1, delta x2 and delta x3. So if delta x1 with x bold, delta x2 and delta x3 are in the directions of the unit normal vectors n1, n2 and n3, then from the just previous equation, that means 27, from the previous equation 27, we can write delta x1 by delta phi 1 divided by delta x1. Equation 27, we can see delta phi 1, delta phi 2 and delta phi 3 expressions. So from there we can write delta phi 1 by delta x1 is delta phi dot n1. Delta phi 2 by delta x2 is delta phi dot n2. And delta phi 3 divided by delta x3 is delta phi dot n3, where delta x1, delta x2 and delta x3, I have already mentioned that these are magnitudes of delta x1, delta x2, delta x3. These x's are bold and these are basically the vectors. So consequently, we can write equation 27 and 28 as, so if we look at equation 27 and 28, from both we can write delta phi dot sj surface vector is basically alpha 1 delta phi 1 by delta x1 plus alpha 2 delta phi 2 by delta x2 plus alpha 3 into delta phi 3 by delta x3. We can do a little more detailed explanation of go for little more detailed explanation of what we discussed. Basically, we are performing the surface integral, and this is basically diffusion coefficient grad phi. Phi is the quantity which can be convected or diffused. This can be for momentum equation UVW, and for energy equation this is temperature, so dot ds. So we can write, we have already written this, capital gamma phi grad phi dot s over j, integration over all confining surfaces j we are evaluating. Now since we said that Sj equal to alpha 1 n1 plus alpha 2 n2 plus alpha 3 n3, and alpha 1 n1 n2 n3 are three linearly independent unit vectors, not necessarily orthogonal. So, and this is the interface between cell P and cell E. So basically eastern side of cell P, I mean eastern face. So del phi dot sj we have written as alpha 1 grad phi dot sj we can write as alpha 1 grad phi dot n1 plus alpha 2 grad phi dot n2 plus alpha 3 grad phi dot n3. And then as we were saying that basically this at two different points, we have different phi, then the gradient of this phi we can write as basically phi 2 equal to phi 1 plus grad phi dot dx. This dx is vector, and this can be written as n dx, and this is scalar. So basically grad phi dot n is given by phi 2 minus phi 1 by delta x. So delta phi by delta x. Following that, delta phi 1 by delta x1, when this x is magnitude, equal to grad phi dot n1 unit vector. Delta phi 2 by delta x2 equal to grad phi dot n2. Delta phi 3 by delta x3 equal to grad phi dot n3. So grad phi dot s, that's what in the last, the slide before, we defined alpha 1 into delta phi 1 by delta x1, alpha 2 delta phi 2 delta x2 plus alpha 3 delta phi 3 by delta x3. These are the special explanations we tried to give from this slide, where we have already equation 29, we have already derived it, that del phi dot sj is alpha 1 del phi 1 by delta x1 plus alpha 2 delta phi 2 by delta x2 plus alpha 3 delta phi 3 by delta x3. Now we have to calculate alpha 1, alpha 2, alpha 3. Now n1, this unit normal vector, can be written as n11, n12, n13, where n11, n12 and n13 are the Cartesian components of n1 and can be easily determined by delta x11 by delta x1, delta x12 by delta x1, delta x13 by delta x1, where delta x11, delta x12 and delta x13 are three components of the vector delta x1. So delta x1 is a vector quantity. Its magnitude is basically this delta x1, and this delta x11, this delta x12 and this delta x13 are three components of the vector, from where we can get n11, n12, n13, which are basically then Cartesian components of unit normal vector n1. Similar way, n21, n22, n23 are Cartesian component of unit normal vector n2, and n31, n32, n33 are the Cartesian components of unit normal vector n3. Then we can write n11, n12, n13, n21, n22, n23, n31, n32, n33 transpose into alpha 1, alpha 2, alpha 3 comes from equation 29, equal to S1j, S12 and S2j, S3j. S1j, S2j, S3j. S1j, S2j, S3j are the Cartesian components of surface vector Sj. So it is clear S1 1j, S2j and S3j are the Cartesian components of surface vector Sj. And from equation 31, it is possible to calculate alpha 1, alpha 2 and alpha 3 by applying Cramer's rule. So we'll do that. We can find alpha 1, alpha 2, alpha 3 by using Cramer's rule, where alpha 1 is d1 by d, alpha 2 is d2 by d, alpha 3 is d3 by d. D is the determinant of the coefficient matrix. If we look at equation 31, so basically coefficient matrix determinant is D, and D1 is obtained by replacing the first column of D by the column with the elements S1, S2, S1j, S2j and S3j. So basically first column will be replaced by these quantities, then we will get D1. Second column is replaced by these quantities, we will get D2, and third column is replaced by this, then we will get D3. And dividing by D, we will be able to find out alpha 1, alpha 2, alpha 3. The diffusion flux is made of two distinct parts: normal diffusion and cross derivative diffusion. The second part arises from non-orthogonality of the grid. The normal derivative diffusion flux of phi through any cell face involves the values of phi at the cell centers, whereas cross derivatives and cross derivative diffusion flux takes into account edge center values. If you recall that every side we defined edges and also edge centers of every side of a cell. Cell center, then cell faces, face center, and then every face has edges, edge center. These are the geometrical parameters we have to make use of. Now let us examine the diffusive fluxes on one of the control volume faces. The gradient of phi at the cell face center can be expressed either in terms of derivatives with respect to global Cartesian coordinates, that is ijk, or local orthogonal coordinates nts. So grad phi can be written as del phi del x I, del phi del y j, del phi del z k, or del phi del n into n, del phi del t into t, or del phi del s into s. Now this vector del x1 then will be given by xp minus xc into I, yp minus ye into j, and zp minus zd into k. These xc, ye and zd, these are defined at the center of the eastern neighboring cell, and xp, yp, zp, these are defined at the cell of interest, that means p cell. And then the magnitude of this del x1 is given by then root over xp minus xc square plus yp minus ye square plus zp minus z square. And the unit normal vector can be given as xp minus xe E divided by del x1 I yp minus ye divided by del x1 into j zp minus zd divided by del x1 into k, which can also be called as n11i, n12j, n13k. So unit normal vector in the previous slide, if you recall, we represented by n11, n12, n13. So this is how unit normal vector is basically n11i, n12j and n13k. The normal derivative diffusion flux is treated implicitly and is coupled with the implicit part of the convective flux to calculate the main coefficients of the discretized equations, while the cross derivative diffusion flux is treated explicitly to avoid the possibility of producing negative coefficients in an implicit treatment. This term, together with explicit part of convective flux, is added to the source term. Progress further with the example of again the eastern surface, and we can see that this is the edge of the cell and this is basically center TE, and this is the edge of the cell center BE, and phi has been defined here, phi BE. The example of east face taken to illustrate the diffusion model. It is shown in the figure. Given the edge center values, as I said, and phi defined there, phi T, phi B, phi AC and phi NE, we can get the normal diffusion term as phi E minus phi P divided by delta x1. This is the distance, magnitude of the distance between the cell center of P cell, which is identified by P, and cell center of E cell, which is identified by capital E. So phi E by minus phi P divided by del x1, this is separated by a distance, magnitude of which is del x1. And the cross diffusion terms are basically phi T minus phi B divided by del x2, phi NE minus phi AC divided by del x3. So we can find alpha 1, alpha 2, alpha 3 by the procedure. We have already mentioned it earlier, that applying Cramer's rule. By applying Cramer's rule, d1 by d is alpha 1, d1 by d2, d1 by d is alpha 1, d2 by d is alpha 2, and d3 by d is alpha 3. By the procedure, as I said, outlined earlier, we can calculate alpha 1, alpha 2, alpha 3, and then we can write that diffusion flux is basically, this is diffusion coefficient into alpha 1, then this is the normal diffusion, phi E minus phi P by del x1, and these are the cross diffusions, alpha 2 phi TE minus phi BE by del x2 plus alpha 3 phi NE minus phi SE by delta x3. So phi T minus phi B by delta x2 into alpha 2 plus phi NE minus phi AC by delta x3 into alpha 3. These are the diffusion fluxes in the cross normal directions, and this is the basically normal diffusion flux. Equation 33. Now this here, when we calculate phi E and phi P are defined by, but T quantities like phi TE, phi BE, phi NE, phi AC are not defined because these are edge centers, and center of the face, it can be defined. Center of the cell, it is defined, but at this center of the edges, how it is to be calculated. We will see in this calculation, for example, tau phi TE. In this calculation, cell of interest, that means P, eastern cell E, this is interface. So eastern cell, enter eastern cell, cell of interest P, and the cell which is at the top of P cell, that cell, and cell which is at the top of E cell, that cell. So these four cells will be involved in basically defining phi T. So phi T is VT by V total dot phi P, VP by V total dot phi T into phi T, then phi T by V total, VT by V total into phi E, VE by V total into phi T. So what is phi T? Basically phi T is the volume of the top eastern neighbor cell of P. So that means again let me say this will be P cell where P is a cell center. This is E cell where E is the cell center. Above P cell there is a cell, center of which is given by uppercase T. And above this eastern cell there is a cell, center of which is given by uppercase TE. It is basically eastern neighbor of the top cell which is just above P cell. So this is VT divided by V total into phi P. We are interpolating. VP, volume of the cell of interest, divided by this total volume. We'll just define what is total volume, into phi T. Phi T, that means the eastern neighbor of the top cell above cell P. Its center is T, phi T. VT, again volume of the top cell divided by V total into phi at the center of the eastern cell. Again VE, volume of the eastern cell divided by V total into phi T, that means phi at the top cell above P cell. So this is VT, VP, VT, VE, cell volumes. This is cell of interest P, its volume. Then this is cell which is basically eastern neighbor of the top cell over pH cell, and this is volume of top cell, this is volume of eastern cell, and V total is volume of that cell which is basically eastern neighbor of the top cell. VT, VP, cell of interest, Vt top cell over pH cell and Ve eastern neighbor of cell P. So this is how phi Te is calculated, involving 4 neighboring cells. 4 neighboring cells, that means cell of interest P, cell above it T, eastern neighbor E, and basically the corner at this on the above P, the cell is T and its eastern neighbor, that means cell which is just at the top of eastern cell, that is T. So we are involving 4 cells to define phi T. Similarly, phi B will involve bottom cell. Here phi T involved top cell and top eastern neighbor. Similarly, when we define phi B, it will involve pH cell, its bottom cell, eastern neighbor and the bottom cell of the eastern neighbor. And then this will be defined through interpolation. Similarly, phi NE will involve 4 neighboring cells, phi AC will also involve 4 neighboring cells, and these are to be defined. So basically that is how these quantities phi T, phi B, phi NE, phi AC are calculated so that we can find out from equation 33 the cross diffusion, and normal diffusion will be given by phi E minus phi P by delta x1. Having done that, we can go for all other cell faces and calculate the complete diffusion from the cell of interest P. Then we consider source term. This is to be integrated over the cell volume by assuming the specific source at the control volume center. Then we can write that volume integral of S phi dV is S phi defined at point P into the cell volume. So apart from S phi explicitly treated, parts of the convection and diffusion fluxes may also be added to this term. Momentum equation contains the very important term, which is pressure. Now this term is also treated explicitly. Its discretization is analogous to that of the ordinary diffusion flux, that is for ith momentum equation, pressure term can be written as P Ni S integrated over S surface, and then for all the confining surfaces we can write summation of Pj Sij minus summation of Pj Sij. Pj is the pressure at the jth cell center and Sij is the ith component of the surface vector for the face J. This is relatively easy to handle. Now having done that, we have evaluated, if you look into the Navier-Stokes equations, now we have evaluated this convective diffusive fluxes at the time level n, that means at the current time level in all the cells. We have calculated the pressure terms, but pressure terms also we have used nth level pressure, but ideally it should have been n plus 1th level pressure. And then we have done mass lamping here, rho into volume, and this is u p n plus 1 minus u p n by delta t. And this u a can be u, can be v, can be w. Then accordingly p has to be adjusted, and these are the momentum equations in 3 directions. This has to be solved along with the discretized continuity equation. Continuity equation has to be this, but at the moment we do not have also value of fj over all the confining surfaces at n plus 1th level. We know at nth level. So at each finite volume cell, due to explicit differences, this scheme suffers from, of course, the time step restriction, etc. We have to follow from CFL condition. Now first, what we do, since all pressure at nth level is available, convection diffusion contribution at nth level is available, we advance it explicitly through this equation, but we cannot write n plus 1 here because we are advancing through a time step delta t, but this velocity, whether it is u velocity, v velocity or w velocity, this has not satisfied continuity equation as yet. So this is basically the equation that we are using to calculate provisionally advanced velocity quantities. And difference between these two equations, basically you can see, we can write in symbolic form. That means rho into v, volume, this v is volume, rho into v, rho into v, rho into v, into difference between velocity at n plus 1th level and the star quantity, which is up prime by delta t. So we are calling just, we are calling it as up prime. We could have called it up correction as we have done in simple and Mach algorithm. But here just, meaning is same. This prime has been used. Minus pj prime sij. Again it is same. Pj prime means pj n plus 1 minus pjn. So this difference in pressure is pj prime, summation over all surfaces. Where the corrections are, so exactly what I said, we can call it velocity correction, we can call this as pressure correction. So up prime is up n plus 1 minus up star, and p prime is basically p n plus 1 minus pn. P prime j is p n plus 1 j minus pnj. And the corresponding flux corrections. So obviously, since velocity is being corrected, so flux also, the mass flux required to be corrected, requires to be corrected, and then this is basically summation of fi prime, fj prime over j equal to summation of f star over j. So this mass flux, if we calculate using correction term, this is mass flux correction, and if we calculate using provisional velocity u star, this is f star. So equation 42 and 44 can be simultaneously solved by the following way. This is as usual the pressure velocity iteration, which we already know from MAC algorithm and simple algorithm. Assume some guesses for the cell center pressure corrections PP prime. Use interpolations to obtain the corresponding phase center correction pressure correction Pj prime. Use equation 42, that means this equation, to get cell center velocity corrections. Use interpolation to get then phase center velocity, phase center flux correction, and compute the convection flux correction rather, Fj prime. Compute the residual, that is basically difference between, in equation 44, these two equations. Left hand side, when there will be no velocity correction, obviously the start quantities have reached n+1 quantity. So basically that is what we have written. Compute the residual difference between RHS and LHS. So there will be no difference when the velocities have evolved to the velocity at a level n+1. We can use this residual to get new values of the corrections PP prime, and improved and faster way of doing this involves, maybe you can use conjugate gradient method and repeat step 2, 3, 4 and 6 till residuals are 0. That is less than a pre-specified value. Care has to be taken that interpolation in steps 2 and 4 are done in a manner such that slow convergence does not result. Experience suggests that some form of momentum interpolation may have to be used in step 4, that means here, instead of essentially the linear interpolation proposed earlier. The procedure based on momentum interpolation is an improvement of the present procedure with respect to speed of convergence. So basically what we can say, that in this process, calculation of diffusion flux, calculation of convection flux, calculation of the contribution from the pressure, these are different than what we discussed about MAC and simple algorithm. In arbitrary geometry, arbitrary control volume, very special procedures we have outlined, but having outlined that, we can define this equation as a projection equation. That means at the next time step, UPn+1 has to evolve, but since we are not using pressure at n+1th level, we are getting velocities which we are calling as provisional velocity, and this is identified by the star mark. And then difference between these two equations will give us a relationship 39 and 41, velocity correction and pressure correction. So pressure has to be corrected so that Pn evolves as Pn+1, and velocity has to be corrected so that up star becomes up n plus 1. And then we have progress from nth level to a level n plus 1. And if this is basically, we have to find out the velocities in a steady flow problem, we have to progress in the time direction till we get same values for 2 consecutive time steps. If it is unsteady, flow is inherently unsteady, then we will have to reach a dynamically steady state condition. So with this, we will finish this lecture today. In the next lecture, we can probably discuss about obtaining faster convergence and few other concepts of relevance. Thank you very much. Thank you.